Series combination of n₁ capacitors, each of value C1 is charged by a source of potential difference 4V. When another parallel combination of n₂ capacitors, each of value C2 is charged by a source of potential difference V, it has the same energy stored in it as the first combination has. The value of C2 in terms of C1 is then A 16 C1 by n₁n₂, B 2 C1 by n₁n₂, C 16 n₂ by n₁ C1, and D 2 into n₂ by n₁ C1. So here we are given a series combination and a parallel combination, and we have to equate the energies of them and find C2 in terms of C1. So for series combination, we know equivalent capacitance C equivalent is equal to C1 C by N. Here it is C1 and N1, and we are given potential difference is 4V. And we know energy of capacitance formula is half CV square. So here we have E1 is equal to half C1 by N1, which is our C equivalent, into V square, which is 4V whole square, which is 16V square. Now we can take the parallel combination. In parallel combination, we know C equivalent is C into N. So number of capacitors into capacitances if it is identical. So here we have C2 N2, and the potential given is V. And using the same energy formula, we can write E2 is equal to half C2 N2 into V whole square, which is V square. Now we have reached the area where we have to equate E1 and E2. So we have E1 equal to E2. E1 is half C1 by N1 into 16V square. E2 is half C2 into N2 into V square. Half C1 by N1 into 16V square equal to half C2 N2 into V square. Now let us cancel the common terms on both sides of the equal sign. We have V square, and then we have half and half. And we can rearrange. Since we have to get C2 in terms of C1, we can take this N2 and move to the other side. Then we'll get C2 alone. So we get C2 equal to 16 C1 by N1, and when taking the N2 from numerator, it goes to the denominator other side, N2. Okay. So we have 16 C1 by N1 N2, which is option A.